So it's a pleasure to have Zvi Shem-Tov give us a talk on quantum ergodicity for arithmetic hyperbolic manifolds, and it's sort of the first. This room is not fully transformed yet, but it's already nice when it used to be. It's particularly nice to have it talk here. Yeah.
Thank you. The talk is about eigenfunctions of the Laplacian on compact Riemannian manifolds. But to give you some feeling of the problem, to illustrate it, I'll start with discussing planar domains. So suppose you have some planar domain in R2, some nice shape omega. On it, you have the Laplacian one, given by dx squared by graph dy squared, acting on functions of it, and we look at a solution to this Laplace equation with the Dirichlet boundary condition that it vanishes on the boundary. We can take an orthonormal basis of such eigenfunctions. The eigenvalues automatically tending to infinity of the volume. And for each of those functions phi j, we define this probability measure given by integrating against the absolute value squared of phi j. So these measures have a very standard interpretation in physics. They give the probability distribution for the position of a quantum particle in states, in pure states, phi j. And so here in the picture, we see two kinds of domains. So one of them is the disk, the other one is the stadium. And these pictures are those, given those measures for a typical sort of eigenfunction with the eigenvalue very high. So we see here a big difference. So for the disk, you see a lot of geometric structure. You see that you have this white towards the center of the disk. Whereas here for this domain, it's called the stadium, basically just a rectangle and two semicircles on the sides. You see a much more chaotic picture. I mean, you see that it's somehow evenly distributed along the domain. So if this room was bigger, you could barely distinguish between those two. And that's the point here. All right. So what's the reason for this difference between the two domains? This is very well understood and is related to the corresponding classical dynamical systems, which is given by a billiard ball that moves in straight lines and follow the standard law of reflection. So here you see typical trajectories of this billiard ball. And again, here you see this geometric pattern. And here you see that it is more equidistributed along space. So this kind of system we call ergodic, means that typical trajectories equidistribute. And basically, this is the reason for the difference we saw before. It's a consequence of that.
Is it related to billiard of Sinai? Is it related to Sinai ergodicity?
To Sinai ergodicity?
Yes.
That is Banimovich study. Banimovich, yeah, Sinai and Banimovich.
Yeah.
Study that.
Okay.
So because of something called the correspondence principle in physics.
Sinai usually is you have remove a scatterings in the middle, and then it's much more clear why it's chaotic. This is a very subtle construction of Banimovich.
And so it is well known that there is a connection between the distribution of those eigenfunctions and the classical dynamics when you take the eigenvalue of the energy to infinity. Now, this, so to say this much more rigorously, and there is this quantum ergodicity theorem of Schnellmann, Zedek, and Colin-Didier, who proved it in various settings independently, okay, which tells you that if the classical dynamics is ergodic, then most eigenfunctions equidistribute, and this most here is very important. That's that. The question is whether you can remove this word most here. So what do I mean by most eigenfunctions equidistribute? You look at weak limits of those measures, mu j, from before. And the statement here is that for a density 1 subsequence, the Wixter limit is going to be the uniform measure on the domain. So the answer to this question is no, in general. You can have an ergodic billiard and still have some weak limits that are not equidistribute. Like this, basically the reason for so those were constructed by Husserl using this kind of trajectories that are called the bouncing ball, which is only mildly chaotic. And now the question is, what happens if we take much more chaotic systems, cause more chaos into the problem?
But the stadium is not an ellipsis. It is
It's not
horizontal.
an ellipse, it's
Horizontal line and semicircle.
Ellipse is
completely
integrable.
integrable.
Ellipse is remarkably integrable.
I see.
Right, it's a wonderful thing.
Oh, because it's piecewise trivial.
No? Leave it as an exercise. The mass problem in Euclidean geometry. Now, confocal ellipses are integrals of the motion. Once tangent of a confocal ellipse, you always take.
So this is many orbits, this is not one orbit.
This is one orbit. It
Oh, all of this is one
like
orbit.
this horizontally and then comes back, and it takes it a lot of time to. So basically,
You do have a one parameter family of closed orbits.
Yeah. How does it come back? Does it hit the?
It's a one parameter family of closed orbits.
So for us, our model for strongly chaotic systems is going to be just hyperbolic manifolds. They have negative curvature. What it means is that if you start with two very close points in your surface, then the corresponding to geodesic can diverge very fast. Actually fast. So this is a picture of hyperbolic surface and typical geodesic on it. And for those kind of spaces, the quantum ergodicity conjecture of Rudnick and Sarnak states that you always have equidistribution. So just to state it formally. So we have a compact hyperbolic manifold. It is always a quotient of hyperbolic space Hn by some discrete group of isometries, gamma. Phi j are, again, eigenfunctions of the Laplacian. And we define the sequence of probability measures in the same way and ask what the Wickster limits are. So here, the role of this billiard trajectory is going to be played by the geodesic flow. So in this lecture, I'm going to focus on a very special kind of such hyperbolic manifolds, which are the congruence manifolds, or arithmetic manifolds. This is the most famous example where you take as your lattice of isometries SL2Z, which acts by Möbius transformations, integral Möbius transformations on the upper half plane. Although in this example, this is not, you don't get a compact space, but still have a finite volume, and you can ask the same question. And this is an illustration of the fundamental domain of this lattice. Now, on those arithmetic manifolds, there is a very special phenomenon that occurs. It was discovered about 100 years ago. Yes. Turns out that there are some additional symmetries other than the Laplacian, which comes from the arithmetic structure of the manifold, or the number theoretic structure of it. So this is realized by the Hecke operators. So what are those Hecke operators? Basically, you look at the Hecke operators are some discrete averaging operators defined by correspondences. Correspondence for us is just you take a point on your manifold X, and I give you a finite set of points in the manifold, and the Hecke operator is acting by taking the sum over those points, this finite set of points. But it's not any set of points will be good for us. It has a lot of geometric structure, and the key point here is that those operators commute with the Laplacian, and so we can take joint eigenfunctions, and we get so-called automorphic forms, which are extensively studied in context of number theory. So this is an example of classical Hecke operator in dimension 2 on the surface. Show you a picture of it. So here again is the fundamental domain for this SL2Z. And if I take a prime number, in this case 3, then if this is our initial point, then this is the set of Hecke points on which we take an average. This is an example of a classical Hecke operator. Now, for this lecture, we need a different point of view of these Hecke operators. We need to define them slightly differently. So for this, so recall again that Hn, this the n-dimensional hyperbolic space, upper space, is an example of a symmetric space, is always given by a quotient of Lie group by a compact subgroup. So this Lie group is a group of isometries acting on Hn transitively, in this case so n1. And if you take the stabilizer of a point and quotient by it, then you get this representation of the hyperbolic n space. Now, this is a real Lie group Okay? But we can obtain it by the real points of an algebraic group G, which is defined over the rational numbers. This is given by a set of rational equations. And when we take the real points, we get our Lie group SON1. So we can do this in various different ways. And this is going to give us various lattices gamma, which are the integral points of algebraic. Now, just like we have this real symmetric space, G mod K, we can get a periodic symmetric space by taking the periodic points of our algebraic group and taking the quotient by a maximal compact subgroup of it, which is the ZP points of our group G. And we have this periodic symmetric space, which is in a way analogous to this real symmetric space. In the case of for dimension 2, you just get the P+1 regular tree. So in the picture, now we also have this G of Z1 over P. This acts diagonally on this product of two groups, and this is a lattice in here. Now, with this notation, we get this presentation of G mod gamma as G times GP modulo this lattice and modulo KP on the right. And this presentation gives us a sort of foliation of G mod gamma of this homogeneous space by many copies of those periodic symmetric spaces. Okay. So for example, in dimension 2, we somehow foliate our surfaces by P+1 regular trees. And the Hecke correspondence is going to just be like the set of points which corresponds to each of those points X is just the sphere, something which I call the sphere in those periodic symmetric spaces. So for trees, for example, this is indeed the sphere in the metric of the tree. And in the other cases, it is sets like this, KP, T, KP, where T is any element of GP. You can see easily that this is finite because this state is discrete and KP is compact.
Does the sphere means set of equidistant points from some center in some metric?
No, but for the tree, yes. More generally, not exactly, but that's how I think of it, and that's how I want you to think. So that's the Hecke foliation, gives you the Hecke operator. So for example, in the two-dimensional case, you exactly get the graph Laplacian, each of those trees. Now, arithmetic quantum ergodicity is exactly the same question, this equidistribution problem, only for those special kinds of eigenfunctions, the Laplacian, which are also eigenfunctions of those Hecke operators, and these are called Hecke Maass forms. So this question, this problem was solved by Lindenstrauss, 2006, for compact congruence surfaces. So in fact, again, this problem considered also for non-compact quotients, like this famous modular curve here. And for this, Lindenstrauss methods only prove that the limiting measure is proportional to the uniform measure, and then that it is actually a probability measure was proved by Sounder Arjan. This is called non-escape of mass. The space is not compact, you have the possibility that some of the measure can escape to the cusp. You need to rule this out separately. Now, the main focus on this talk is about this question, but for higher dimensional hyperbolic manifolds. Now, what you can think is, okay, so Lindenstrauss proved this. Can we use more or less the same methods or the same ideas to prove it in higher dimensional case? Though I didn't tell you anything about the proof. So the point is that that in a higher dimension, there is a new feature. When you take a larger group, you have many intermediate subgroups that can cause problems. That those measure rigidity techniques of Lindenstrauss basically do not see. So here is a very typical problem. So forget equidistribution, forget anything. You just have the limit measure mu. Right? If it is the uniform measure, then of course it gives measure 0 to any submanifold of lower dimension. So prove that for every totally geodesic submanifold of codimension 1, this measure is 0. That's the typical problem that we want to understand. Now, so for surfaces, dimension 2, those totally geodesic spaces are basically closed geodesics. And to show that they have measure 0 follows from some positive entropy estimates done by Bourgain and Lindenstrauss that were actually part of this whole machinery of Lindenstrauss for proving that the measure is uniform. So in the sense that this comes from free if you already have what you need to apply all those techniques. Notice also that in this case, those closed geodesics are small compared to the ambient manifold, at least in the sense that they have dimension, they have half the dimension. But if we take the bigger dimension, right, then those one codimensional manifold is going to have much bigger dimension, the ratio. So in 3 dimensions, showing this is one of our main results, showing that for 3 hyperbolic manifolds, the limiting measure of
You do it for 3 dimensions. Which arithmetic manifolds are you dealing with? All arithmetic or special arithmetic?
all congruence
They come from quadratic forms, or they could come from. There's a classification that's quite complicated of arithmetic.
of congruence manifold. I can.
Which ones did you deal with? That's the question.
I take risk. You take.
I'm asking, he needs to start somewhere.
SL2 over number fit. We take any form of SL2, and we take the restriction as scalars.
So there's some funny forms that come from TITS.
I think basically as long as you can present it in one way or another as G of Z, I can handle it.
They're going to be arithmetic. I'll give you an example of a problem that was solved for quadratic forms and for all forms that you are thinking about. This problem of Agel, that Agel eventually solved this. Every hyperbolic 3 manifold, there's a finite index subgroup. come up with a positive Betti number. Even in the arithmetic cases, this was not solved, and the one missing case was exactly these very exotic forms of teats. So I'm just saying that I'm just alerting you to this fact that there are some, and nobody ever has made that work in those cases.
What are those forms? I mean, if you give me,
They come from some division algebras of certain types, which with some accidental thing becomes
So
SL2C.
the question for me is that.
I'm not saying your methods don't work.
Right,
I'm
yeah,
just saying,
no.
Yeah.
All right, yeah. I mean, yeah, what I'm trying to say is that our methods are very well defined in a sense. So if I know the definition of your life, I should know immediately.
Right, and then, but I'm just saying that many, Raghunathan, Blavatsky, all of these guys fell into this trap of claiming that they can produce conjecture for all hyperbolic manifolds, which are arithmetic, and these were shown that. And it's got to do with totally geodesic. So I'm just saying that you, they could. I've got a red flag in my head.
All right. So
but your methods, I would imagine. I'm just saying.
Once I see the definition, I can tell you, I guess. So you mentioned.
I'm doing a Borel on you. Okay, I'll do it. I could have been ready before when you talked about GZP. He would get very excited when people would put GZP.
Oh, really?
Yeah, there's several definitions.
Yeah, of course. I
got a whole
paper. Yeah, it's not always possible to take GZP. I like that.
I'm familiar with it.
So in dimension 4, in any single case, we can't rule this thing out. And that's the only barrier from proving arithmetic QUE in this case. This was very specific kind of lattices, obvious ones. Now, interestingly, if you look at in 4 dimensions and you look at 2-dimensional submanifolds, then this problem, then showing that the measure is 0, turns out to be much, much harder than this. You have to use much more delicate things, right? So this already tells you that looking at the dimension is not the correct way to measure how big is the sum. Okay. So that's where the difficulties come from. Now, before I explain our methods and what we actually do, let me just state the results. So again, here I am I'm not claiming anything about what kind of lattices there, rather than there are congruence lattices.
You're taking a quaternion algebra. You meant a quaternion algebra of a number field, and that's with many copies of H2. Yeah, that's fine.
Yeah, maybe more than yes, at least that. Okay, so as you said, so again, not only for hyperbolic free manifolds, but for products of R copies of H2 and S copies of H3, or in other words, SL2 over number fit. So for this case, we completely prove quantum unique ergodicity, including non-compact quotients, because the original argument of sound for the 2-dimensional case just more or less works in this setting as well. Now, for 4 dimensions, we don't quite get QUE. Again, but we put very, I would say, strong constraints of the measure. So that's what we prove. We prove that any limiting measure must be a countable convex combination of either the Haar measure, the uniform measure, or some uniform measures on 3-dimensional hyperbolic submanifolds. So in particular, if you can show that that any of them has measure 0, then you prove the QE. Also here, this is not just a linear combination. I wrote convex to emphasize that here as well we solved this problem of escape of mass in the joint work with the Faveri. Although here the showing escape of mass becomes a harder problem. So in the two-dimensional case and in the three-dimensional case, the main tool for showing it is taking a Fourier extension of your form with Fourier coefficients an and using the fact that they satisfy some relations of this form. And in those works, they use substantially of the fact that those relations are bounded in the length. So the nth coefficient is expressed as a sum of two other coefficients. It completely breaks down starting in the four-dimensional case. Then you get those kind of relations, but with unbounded number of terms, like linear in P, at least in 4 dimensions. So you have to find some more cancellations.
In your work, let me ask you a conceptual question. If you were a physicist, you would go to the phase space.
Yes.
And you go to the group where you haven't discussed the microlocal lift, but you're proving a much stronger theorem. You're proving that the microlocal lifts are equidistributed. Do you relate them in higher dimensions to the physics phase space? Or do you just discuss it?
No. I mean, because because I only restrict myself to hyperbolic manifolds here.
No, there's still a unit tangent. I mean, the question is, if you want to think of it physically in higher dimensions, then you should go to phase space, which is also always well defined for the geodesic flux. So then
I just cautioned here that take.
Yeah, but there's a difference in SL2. These are the same thing, but when you're in higher dimensions,
You have the frame flow.
No, but
right. So I'm asking.
But I mean, how?
But I can.
If you have an eigenfunction of the Laplacian, when you lift it, it sort of naturally would. I mean, the only way I know how to lift it would be invariant under this difference between them. So basically, it's a trivial lift from the.
In this case, exactly, you have this.
If you look at Colin de Verdier's theorem or Silberman, that's got nothing to do with dimension. So you have phase space. I'm just saying.
I know. I mean, I can.
I'm saying that I don't know how to phrase a question about the frame bundle. I mean, the way I know how to lift eigenfunctions to the frame bundle is by trivially averaging over this S.
But why not to G mod M?
Yeah. So I'm just saying,
yeah,
right.
I get exactly the phase space.
Right, so I think your theorem contains that state.
No, I think
that's
it's not. No,
I think you have a refinement.
I don't think so. I think it's basically, I don't know how to lift eigen. I mean, the question is how to do this microlocal lift. So the microlocal lift you do is automatically invariant under this M.
So you can push it.
So it's basically I don't know how to do. Basically, only I don't know how to get some kind of inputting statement about the frame flow.
Okay. Anyway, I think I'm just pointing out this is something you should have a good answer to. I give Zeldich in the audience.
I think
what's a microlocal lift?
That's
well defined.
If I take here instead of K, if I take M, then I get exactly the place.
Yes. Yeah. So I think.
All right.
Right. So I think you contain. I think you have more information.
That's not.
I don't think of more information.
Right. Yeah.
I want to follow. Your point is that the equal distribution is actually on something a little bit bigger.
Yes.
Okay, because they're working algebraically.
Yeah.
You're pushing out.
Right. So I'm trying for him to relate the phase space to what he's dividing. Which in SL2 are the same thing.
Yeah.
Because the unit tangent bundle is SL2.
Yeah. It's just fine.
But in general, it's different.
It's bigger. I see.
And so it should be discussed. That's all.
I do claim that my result contains it.
I also think so. But anyway, you should think it through. That's all I'm saying.
Once you get.
I think that's for sure.
I mean, the natural thing is to lift, I mean, this is Silberman's thesis. I forgot, I'm sure I discussed it with him, but the natural thing is to lift it at E.
And that's what.
Once you're doing Lie groups, but since you started out by explaining
I know.
phase space, you should connect it.
Yeah, I thought maybe I should.
Somebody will ask you this question as you tour the world.
So my answer to it is yes. Thanks.
Yeah, so I think it through. Yeah, we can discuss it though.
Okay, so the microlocal lift
Here we go.
is a very important construction in this context. Due to Schneiderman, at least.
It's Schneiderman's definition.
And what you do, it turns out that, okay, so I'll just state it in this setting. So because you have this presentation of your space, then you have this bundle G mod gamma, and the statement is that every weak limit you can lift to this space. Okay. So it projects onto mu, this lift, this mu tilde. And the important property of it is that it is invariant under the action of a certain subgroup. So homogeneous dynamics comes into the picture. So what is this subgroup? I call it the geodesic flow. It's a one parameter diagonalizable subgroup AT. So if you think of SL2, it's just a group of diagonal matrices. And if you think of SO1N, it's again a group of diagonal matrices, one parameter group of diagonal. And then the other important property, because we only know how to treat arithmetic settings, then the thing is that what you get can be represented as a weak limit of measures coming from eigenfunctions of the Hecke operations. We don't need the Laplacian anymore, but it's important that our limit on G mod gamma, which we now consider, comes from eigenfunctions of Hecke. And in fact, that's exactly what we're going to do. We're going to show that those weak limits are necessarily uniform. So in particular, mu is uniform. Okay. So now, one approach, once we have this microlocal lift, that's exactly our approach, is to try to classify what kind of AT invariant measures do we even get. Okay. If the geodesic flow, this place there was a geodesic flow, and I told you this is ergodic and very, very chaotic. You might think that there is no A invariant measures at all that are other than the uniform measure on G mod gamma, and similar statements are indeed true if we would consider different kind of flows, unipotent flows. We have Ratner's theorem. So the bad news is that in this case, there are plenty of AT invariant measures that we should try to rule out. So the very rough distinction between those invariant measures are, so there are nice invariant measures, which are basically homogeneous measures. So those are just the measures that are supported on orbits of nice subgroups that contains this AT flow, and also convex combinations of those homogeneous measures. But on the other hand, there are those not so nice measures. Okay, so this is not very hard thing to see that in the case of this geodesic flow, you have orbit closures that are actually fractals, Cantor sets, things like this. And the way you should think of the measure rigidity technology, Lindenstrauss and Alexandre, is that it tells you that if certain non-localization properties are true, then you can be sure that your limit, that your measure, your AT invariant measure, and this has nothing to do with limits of eigenfunctions, okay, is a convex combination of homogeneous measures, so it's nice. So in the case of two-dimensional surfaces, this almost enough to show QUE, because you don't have many nice measures. Basically, the only nice measure that you have is the uniform measure, and maybe measures that are supported on closed geodesics, and we already said that this we can rule out in today's perspective quite easily. But as soon as you go to higher dimensions, the family of those nice measures become very, very big, and that's the main source of difficulties that we. So again, so there's those conditions that are specified in this theorem, which is a generalization of the original measure classification of Lindenstrauss. I just say that in ongoing projects, we're not actually using any of those results as is. We sort of go through the arguments themselves and take what we need. So there are some redundancies here, which you might see. So the first condition is called recurrence, just maybe the most important condition, although it's the easiest one to prove, and it's true in general for any symmetric space. Just gonna ignore it. The positive entropy condition on almost every body component is very challenging. I'm not gonna define what entropy is. For us, basically, what you should think of is that epsilon tubes of your flow decay polynomially with epsilon. But here, again, we have a new difficulty because the centralizer of the flow is not trivial anymore. And in fact, in the sense that I'm gonna discuss soon, it is very big. So this condition, which is completely necessary today, is for these methods. So this we don't know, we don't have any clue to prove it or if it's even true in any dimension that's bigger than 6. Dimension 5. We know how to show. And also these conditions, no non-exceptional returns that I'm gonna just skip. Okay, but now what I want to focus on is that suppose that we have all those non-localization properties, and then we have this conclusion of the theorem that our measure is a convex combination of homogeneous measures. How do we show that the measure is actually the uniform measure? And the methods I'm going to discuss now are more or less related also to showing those two conditions. So how do you prove non-concentration? So I'm gonna be a little bit more technical now and speak a little about the proof a little bit. So suppose you have a homogeneous measure and it is supported on some nice subgroup H like this. One thing you can show, it's more or less standard, is that since this is periodic, it is contained in a set that looks like this. So this, it might look like an orbit of a nice group, but it's not. H0n is not a group, and it's crucial. I mean, because this H0 times n is not a group, all of the methods that were used, the methods that were used by Bouguer and Lindenstrauss for the entropy and everything fails basically. So you have to deal with this fact that it's not an orbit of a group, but rather some kind of a packet of orbits or a union of many, many orbits. So here H0 is some rational subgroup of G. It means it's defined by rational equations containing the flow. And M is a compact subgroup, which is a copy of SO n-1. So here again, you can see the degeneracy of the case n equals 2, which makes M trivial. Right. So we have this, and since there are most countably many such sets, it's enough to prove that the measure of each one of them is 0. And how do we do this? So another observation is that you can look at M and say, okay, it's a compact subgroup. How bad can it be? So the point is, it can be very bad. I mean, M, although it's compact, we're going to look at the periodic capacity that it becomes huge. Okay, so what I'm gonna talk about now is something called the amplification method. I think the term and the method is due to Donna or so the very basic idea comes standard by now.
In this context, we introduced.
In this one, is to take a Hecke operator tau. Okay, so this is an averaging operator. You sum over some translates of it. And so because and you can expect that because you do this, you somehow what you get, the mass is controlled by the intersection pattern of those translates neighborhoods that you take. And epsilon here is my notation for an epsilon neighborhood of the set L. Okay, and on the other hand, if f is an eigenfunction, then on the other hand, you can divide by the eigenvalue or some power of the eigenvalue to get a rough bound like this. So you can bound the mass of an epsilon neighborhood by some function that depends on the intersection pattern of the Hecke translates of this neighborhood over the eigenvalue of this operator. Now, if you look at this intersection and take S prime to be 1, you can see that the condition that this is not the empty set is that S is contained in this set. Now, if L is a group, or at least a piece of a group containing the identity element, then again, you get some small neighborhood of a group. And then you can apply the Fountain arguments to show that your counting problem, to reduce your counting problem to a genuine subgroup, which is very similar to that. So now if you want to apply this for those, then you can just use the fact that there are not very many rational points that intersect the torus. But if your group is not a torus, it becomes much harder. So that's the summary of this method. You basically want to construct some Hecke operator, which on one hand, you can control the intersections of those Hecke translates. The other hand, you want the eigenvalue to be big. Now, to deal with those large subgroups that I told you about, which are not tori anymore, okay? You have to have some much more delicate method. At this point, I wanted to relate it to another problem, which on first sight seems completely unrelated to it. This is the Sup-norm problem. The problem is to give non-trivial upper bounds on the N infinity.
So of course, Ivanic and I did this, and then when Elon was trying to make positive entropy, I didn't realize that he secretly knew that once he gets a little bit of entropy, he could go the whole way. So of course, Rudnick and I did this calculation just to show you can't concentrate on a periodic.
Right.
But we didn't feel like quantifying it because
Right.
there's some small, but he had a little secret up his sleeve. So these are very related. What he did with Bergan and what he managed, they're very. We just never saw. I saw no point.
This is the first place where I even mentioned something quantitative, right?
Yeah.
For that. All right, so in general, if you take epsilon equals 0 here, then this is a general upper bound for the eigenfunctions on symmetric spaces where n is the dimension and r is the rank. So for example, for surfaces, this is lambda to a half, but you can get an extra very explicit epsilon, that the first result in this direction of Ivanets and Sarnak. And Simon Marshall considered a much more general setting than just surfaces. He took a general symmetric space. So here's a theorem due to Marshall. If you take a simple Lie group G and require some Lie theoretic assumptions, it is quite a split. It is not isogynous to SU and n minus 1. Then you get that this power saving. So this is, so what's the essence of those requirements? So first of all, note that in our situation, if we take G to be SO14, for example, then this theorem fails. It is not quite split. It is related in a different manner. So those conditions on the Lie groups and the Lie group G guarantee the following. So if you take H to be a subgroup of G, such that H of R is a maximal compact subgroup of G, that's what Marshall considered, then the conditions of the theorem tells you that H, right, the algebraic group H, the rational group H, is weakly small, is small in a certain sense. In what sense? So loosely speaking, what it means is this. So again, we have this periodic spheres here, and this is a finite set. You can give an expression for its size. What we want that if we take the sphere for the same element T, but in our periodic subgroup HP, then the size of this sphere is at most square root of the size of the sphere in the bigger group GP. So in fact, what Marshall needed is something slightly stronger than this. He wanted some power saving here. So this condition is more well known as being tempered. This is slightly more than, right? So using this, and there is a way to make this a global definition. So to guarantee that in terms of the algebraic closure, you guarantee that this is satisfied for positive proportion of primes, and that's what Marshall uses. And the point that we use those kind of techniques of those counting methods of Marshall in the context of QUE, and we show that if L is indeed weakly small, then we have this polynomial decay for the epsilon epsilon tubes. It seems very different from estimating how big is the value of 1 point. And so this in particular shows that the positive entropy condition is satisfied if this centralizer of the flow is weakly small in this sense, which breaks down starting dimension 6. Now, recall that we didn't want to show that that an orbit of a subgroup has measured 0. We had something which is not a group, and I told you this is important. So in fact, if this is not a group, all of those results just completely fails. You can't amplify because the epsilon neighborhood, once you take the product with its inverse, you get an open set. And Hecke translates are equidistributed. So you can't expect just counting arguments will give you anything in this for those kind of sets. And what we do, we found a nice argument to deal with this, which is the main point of our 3D results. It turns out that you don't have to count everything. You don't have to count all the returns, just some of them, the ones that we call parallel. So you have two kinds of returns to your epsilon tube. If the intersection looks like this, it intersects in a lower dimensional manifold that turns out that you can deal with it by induction of the dimension. You have to be very careful because many parameters there have to be uniform, but you can do this and reduce the problem to count what we call parallel intersections. And so the final result, which lets us prove that those measures are zero, is this theorem. You take your set L that you want to show its measure is zero. If you show that each of its real subvarieties L prime has rational stabilizers that are quickly small in some sense, in this sense of Marshall, then it's measured by this polygon. So now, finally, I want to discuss, so what should we expect for those subgroups that are not quickly small? So there is this, there is a very well-known construction of automorphic forms, which are lifts from smaller groups. And they're known to have very odd properties. So, for example, people have used them to construct sort of counter examples to in the Sup-norm problem to construct sequences for which the Sup-norm is much bigger than the generic expectation. Okay, so in 4 dimensions, SO13 is not small. That's why we can prove QUE. Instead of the half in the exponent in the definition of weakly small, we get 2/3. However, for certain kind of lifts, we were in a work in progress with the Faveri. We can show QUE for a density 1 subsequence. But this uses the fact that this specific sequence violates the so-called Ramanujan conjecture, so it is not non-temporal. So on the other hand, so what's happening is
the naive Ramanujan.
The naive, the very good. So the question is what happens with the remaining eigenfunctions in those very specific constructions. And also in a higher dimension, basically I don't see any reason to believe that those limits cannot be concentrated on those very large manifolds, but that I don't have any way to justify it yet. I'll stop there.
I have a naive question from a physicist. A physicist would be wondering what happens if you take your stadium and make a three-dimensional object by rotating it like a tube with 2 spherical cups. That is something where you could study eigenvalues and eigenfunctions of Laplacian, and I'm not sure about integrability, but what about ergodicity?
About ergodicity for this rotation.
No, the minute you rotate,
Huh?
the minute you ever rotate, then
Yeah, well, you take horizontal axis and make rotation
Yeah,
around
right.
it.
So if you
You
take
take
the surface
cube,
of
cylindrical
revolution.
cube.
No, but you can take a tube a flat cylinder and attach to it something at the side.
Yeah, you can make it more
Take
complex.
Then you can make it harmonic.
And
That's
attach
what
to
any
it.
study is in this thing, right? Or,
He made
that,
positive
and
entropy,
there
yeah.
you could see the
Yeah,
same.
but they're not
phenomena
surfaces.
that you
I'm
have.
just saying it's not rotation. He's got a way of giving a geodesic flow, a metric on S2 for which a geodesic flow is ergodic and positive measure entropy. That's correct. So yeah, you can ask. These questions are very hard to answer because the physicists have everything physicists claims on this problem is false.
Well, they adapt
Everything. In other words, if you say chaos implies QUE, that sort of thing, I think is false. We know it's false in certain examples. Or if you ask about the eigenvalues where they should behave like random matrices, that's definitely false.
Mhm.
But it's generically true. These things are probably generically true in the space of Hamiltonians. That's probably.
For the physicist, it would be like that. There is a set of classical trajectories, and the quantum probability, which is square of a function, is peaked around each trajectory. So you
Right.
have measure which is
Right, but the point is that each in this very strongly chaotic, negatively curved setting, each closed periodic orbit is isolated and unstable. You can't construct a quasi-mode around it.
I see.
And so people from the beginning thought that you could not see the relation between classical and quantum mechanics in this limit. But when people started to do numerics and you saw those pictures in the beginning of the stadium, physicists got very confused. They thought that you can concentrate on these periodic orbits. Faveri, Hecke, and Rudnick and I went against the grain. People think we just made the obvious conjecture. Actually, nobody believed us at the beginning. I remember they all saying, "You're wrong. We can prove that."
My understanding is that you were trying to actually show the physicists right, with examples that you.
The ones, right, there are these lifts, exactly these lifts that, to me, the obvious candidates for counterexamples. And then I was able to prove QUE for those exact ones. And we began to understand it's true because above plane, Elon's theorem follows from the Riemann part. So we had no doubt about it.
But you didn't prove anything for higher dimension in my sense.
No. In the minute you have something that's mixed.
But you can, the kind of phenomena seen in the Newmovich stadium, you could also see in a closed surface, which is somehow in a smooth way, you glue a cylinder to some.
You're saying you could make it in three
Happen to
dimensions.
see
You
it,
could
yes.
make it in three dimensions. But his methods will not work there, but probably.
No, my method, no, there's a counter, this Hassel method we use.
Still two-dimensional.
But the Hassel thing is, everybody, he just gave a proof. Everybody was aware that you do numerics, they call bouncing ball modes. And you concentrate, so there's a thin subsequence which concentrates on these bouncing balls.
But with numerics, there must be instabilities because if you make a little violation of symmetry, then it will become ergodic.
It's already ergodic.
The stadiums are good. So when he drew the graphs, McDonald and later Hecke, they saw these. You go back to the very first picture. We're back on picture one. So
I have personal interest in quantum ergodicity because I filmed something like that in my work which I reported here.
No. The stadium. Yeah,
Yes.
we don't go back there. Yeah, so there. No, go back. Yeah, that. Hecke had the examples where you had much more pronounced. You can see there's a periodic orbit here, and that's enhanced there. Slide
It's
enhanced.
higher density.
Yeah, it's got a higher density there. And so he was seeking these, and that was surprising to him. And this became known as scars. And whether scars persist in the limit was, he claimed he could prove. And numerically, he was claiming he was seeing them. But once we started to question it, they changed their mind quickly. It became
So it is not
something called
uniformly
mesoscopic, whatever that meant.
So let me get it straight. The stadium is not uniformly covered even in the limit of higher eigenvalue.
Right, the stadium has these bouncing ball things. But other than the bouncing ball things, it's possible that everything else distributes. But the whole point here is to take something genuinely chaotic in every sense with no one parameter family of closed orbits. And then it seems like in the quantum level, you don't see the periodic orbits. The periodic orbits are gone. Completely gone in the semi-classical limit, which is what I think
classical approximation simply doesn't
is wrong. Exactly.
That's interesting.
Yeah, that is interesting. Yeah, that's interesting. When are you leaving? When are you leaving?
I'm flying to Israel in tomorrow, basically. But I come back in a week.
Are you here tomorrow? Let's check.
Oh, no, tomorrow. Oh, yeah.
I'll leave
I
it.
can do that. All right.